Okay, so thermodynamics is a pretty lengthy topic. There's lots of pieces to it that you'll have to know sort of what is being asked of you. Enthalpy is what really we're going to focus on, and we can calculate enthalpy a variety of ways. So all three of these lectures are going to go through each of the ways that we can calculate enthalpy, or which is considered a heat of a reaction. So I'm not sure we're going to get to one of the first ways today, but we'll go through all of them. So the only tricky part really is getting through, like, what is the question asking you, what information is it providing so that you can find the enthalpy of a reaction. And there's, like I said, lots of ways. This tends to be everyone's favorite topic, and some people will choose other topics, but out of the big ideas, thermodynamics tends to be one of the more interesting ones. And it's not that hard to handle, but there's a lot of math involved, and most of you are really good at math, so you enjoy this topic because you have a definitive answer in front of you, and there's not a lot of theory involved versus a lot of calculations, so you probably will enjoy that part of this compared to what we've been doing. So the first part, thermodynamics is the relationship between chemical reactions and heat, what causes chemical reactions to occur, and the concepts of enthalpy, entropy, and free energy. So we will get to eventually entropy and what's called Gibbs free energy at some point, but really we're just going to focus on enthalpy right now, and then that all has to do with energy changes. So heat and temperature are different. Temperature is solely kinetic energy, right? If kinetic energy increases, then temperature increases. We looked at that when we did those heating curves and cooling curves. And so kinetic energy and heat are temperature are directly proportional, whereas heat is a form of energy. So we'll supply heat, we can give off heat, but temperature changes are solely due to kinetic energy changes. So if I double the kinetic energy, then the temperature will double. If I half the kinetic energy, then the temperature would be half. So there'll be some questions in your homework and a little bit with multiple choice that discusses what happens to kinetic energy and then your temperature. Remember with your heating curve that we could still be supplying heat to some sort of solution or compound, but the temperature wouldn't go up. Why is that? Remember on the heating curve it flattens out? Why is it flat? Yeah, change its state or change its bond. So you're using that energy to weaken or sever the intermolecular forces, and so the energy is not being used to increase kinetic energy, which in turn would increase the temperature. So we can still supply heat to something without having a temperature change occur, and we saw that with the phase diagrams. So this is a Boltzmann distribution curve. We'll see these throughout the course, so it's kind of important to understand what all these little peaks mean. So kinetic energy is increasing, which means that your temperature is increasing. And this is the number of particles that are doing it. So envision all of us as the particles in the room, and we're at a specific temperature, 250 Kelvin. So at 250 Kelvin, we have a specific kinetic energy, like we're moving around, right? But we're not all doing the exact same thing. So maybe like I'm over here because I'm wild and running around, right? Whereas perhaps Nelson is over here on the lower end of the distribution curve because he's very mellow. So the distribution curves don't mean that everything is doing the exact same thing. It means on average, most of you are here. But I'm over here and Nelson's over here. Get that? And the same thing happens as we continue, as the temperature increases at 1,000 Kelvin, kinetic energy is increasing, our distribution gets even larger. So maybe like a bunch of you are joining me down here on the crazy end, and then a bunch of you are joining Nelson on the mellow end. Following? So our general average now has decreased because the distribution has gotten larger. So you'll even notice that some of the particles are still behaving all the way down here like they were at 250. So the general distribution gets larger for the number of particles that are doing a variety of things. And so the curve is you're going to see the number of particles doing that getting lower. Are you following what these curves mean? So it's just on average what the particles are doing. You'll see these throughout the course. So it says this is the distribution of kinetic energies. that increase as temperature increases. The average kinetic energy of the particles in a system increases as temperature increases. But just as a really key point, not all the particles do the same thing. They're distributed. All right, energy transfer between systems. So, really key point that I'm going to highlight now is that heat is transferred, not cold. I missed an R. Not cold. We don't transfer coldness to one another. Like if you're holding someone's hand that's really cold, you're transferring your heat to their hand and it's warming up. And it's taking the heat out of your hand, perhaps cooling the temperature of your hand, but they're not transferring cold to you. They're transferring heat, because heat is the form of energy. Cold is not. So when we look at particles in a system, we're going to examine the heat that's being transferred to them. So it says two different systems at different temperatures that are in thermal contact with one another will exchange energy heat. The energy transferred from system 1 is equal to the energy transferred to system 2. So if I have system 1, which is at 350 Kelvin, and I have system 2, which is at 450, and they come into thermal contact, which means like you basically just have, I don't know, let's just pretend like two boxes, plastic boxes holding next to each other. Anything, even like someone's hand temperature, it's the same idea. It's just that they're in contact with one another. So when they come into contact, you can see by my velocity vectors, some of you are not in physics yet, but the larger the vector, the arrow, that means the more kinetic energy that it has. So if I draw little arrows, it means low kinetic energy. If I draw big arrows, it means big kinetic energy, and we know kinetic energy is related to temperature. So in the 450 Kelvin, I should have big arrows, and in the 350, I should have small arrows. Everybody great? So when these arrows, basically when they're bumping into each other, the particles are hitting the walls of these containers, and this one's hot, and this one's hot, and this one's cold, it's going to transfer some of that energy into the other container. And so at the end of this system, they reach thermal equilibrium. And so then the temperatures would remain the same. This is in a sort of vacuum in a sense, vacuum meaning like there's nothing else around it. Because obviously we're going to talk about the surroundings of something. So this is assuming there's no surroundings, there's no temperature being lost to the surroundings. But clearly it could lose temperature to the surroundings because the surroundings would be less than 400 Kelvin. But in just this system by itself, it's going to reach thermal equilibrium and stay there because there's no more heat being transferred. No heat in, no heat out, so it just sits in thermal equilibrium. Yeah, that's it. All right, the law of conservation of energy is the same as the law of conservation of mass, except you just change the word energy. It cannot be created nor destroyed. It is conserved or transformed from one form to another. The energy of a system changes during a chemical reaction, a phase change, or a change in temperature. This results in energy being transferred into or out of the system in the form of heat or work. So I just want to mention at this point that all different molecules and compounds have their own amount of heat associated with them. So some things that require a lot of heat to heat up, like water, that requires a lot of heat or energy in order to make it boil. But if I took a piece of copper, copper pan, and I started heating up, that would heat up very quickly due to the metallic bonds and the electrons that are transferred. So we're going to start eventually, not this lecture, but we're going to talk about something called specific heat capacity. And I just think it's important to mention it now because you recognize that some things heat up faster than others, right? We all know that. You know that you can touch something and it gets piping hot before other things do. So water and copper is a great example of this. So certain things have their own amount of energy related to them, and that has to do with the types of bonds that are involved in them. So metallic bonds, covalent bonds, and so forth. All right, the system and the surroundings. So where a reaction occurs is what we're going to say is the system. Where the surroundings are is the entire universe outside of the chemical reaction. So universe meaning like everything. So if I do a reaction, I'm going to just draw you a little picture here. Here it is. This is where my reaction is taking place. I can't see this, but this is where the reaction is taking place. everything on the outside is going to be considered the surroundings. And then this is going to be considered the system, which is just where the reaction's taking place. So we can't physically pinpoint that spot, but we know what kinds of things are considered the surroundings. So like take, for example, a reaction in water. So I have a beaker, and in it is some water, and I start a reaction. Say I do a precipitation reaction, or even I just dissolve salt in there, right? We don't really say that as a chemical reaction, but in a sense it is, because you're breaking bonds and forming new ones. Remember that? And there is energy transfer related with that. There's going to be a heat transfer. So in a sense, that is a chemical reaction. So say I dump in sodium chloride. And now all of a sudden I have bond breaking, and I have intermolecular forces between dipole ion interactions in there. So the reaction that's taking place is just this, but the surroundings are everything else. So my surroundings here are going to be considered the water, the beaker that it's held in, and all of the air around it. That's my surroundings. But the reaction, this, is considered the system. We can't see that. That's just where the reaction's taking place. It's in the system. But we can visualize and understand that the surroundings are everything else that are around it. Because then we're going to start measuring and discussing where does the heat go, and what's absorbing the heat, and what's releasing the heat. And so in this example, we're going to do a lab with this, where we're going to discuss the water's temperature change. So if we know the temperature change of the water, if it goes up or down, then we know what's happening to the reaction. The reaction is either giving off heat or taking heat, right? So you can really measure the surroundings to determine what the reaction's doing. Should they be the same or opposite? So, for example, if my system is giving off energy, then the surroundings are doing what? Are they giving off or are they absorbing it? They're absorbing it, so they're going to be opposite, right? So if this is absorbing heat, then this must be giving off heat. Or if this is giving off heat, then this must be absorbing it. So they're going to be opposite of each other. So the system and the surroundings are opposite of one another when we're measuring them to see what's happening in terms of an energy change. So the surroundings are the universe, basically. All right, change in a system's internal energy. You're not going to use this equation, really, except that it's going to help you understand how energy changes occur with relation to work. So you will see this on your homework, but it's just meant to help you understand how it's all going to work. I will not give you these questions on a quiz or on a test. There is nothing in the AP exam that suggests that you have to know how to use energy equations or work equations or power equations. But you do have to understand how energy is transferred from a surroundings to a system or vice versa. So this will just sort of help you understand that. So delta E is the change in potential energy and kinetic energy of the particles in the system. Q is the heat that's transferred into or out of the system, which will be a positive value or a negative value. W is the work done on the system by the surroundings, and it's going to be a positive value if energy flows into the system, or work done on the surroundings by the system will be a negative value. So here's what you need to take from this. Is this sort of starting you off with understanding your signs. If there's being work done on the system by the surroundings, and I'm going to show you some pictures of this, then that's going to be energy going into the system. So the surroundings, all on the outside, are giving energy into your system. So it's absorbing energy, which means that it's a positive value as it goes in. Positive values indicate endothermic reactions. This means that it's absorbing heat. And then if it says work is being done on the surroundings by the system, so here's my system, and it's going out, that's going to be exo going out would be a negative value. So negative values are exothermic values, or an exothermic reaction, and this is releasing heat. So when we look at kinetic energy and potential energy here and here, kinetic energy is the actual movement. So this is the bonds are vibrating, they're rotating, the bonds are moving. Whereas potential energy is the energy stored in the bonds. So kinetic energy, if you remember from physics, is energy in motion, right? Potential energy is always stored energy. So we're going to talk a lot about potential energy and kinetic energy in bonds, whether it's more kinetic or more potential energy. And then that will help us determine if a system is endothermic or exothermic. So heat and endothermic processes. In an isolated system, energy is conserved. That means that we're not losing heat or gaining heat from the surroundings. It's just in this little reaction that we're doing. As the bonds in the products contain more potential energy, so they're just showing you, just visually understanding large potential energy in your products. The product molecules must contain then, therefore, less kinetic energy. So I'm not losing energy, and I'm not gaining energy in this system. I just have a certain amount of potential energy and a certain amount of kinetic energy for this whole system. So potential energy is low here, kinetic energy is high here. Therefore, then potential energy is high in my products and kinetic energy is low in my products. So if this is the scenario, and then the products will produce an endothermic reaction and they're at a lower temperature. Meaning delta H is your enthalpy of a reaction, which tells you how much heat there is. So when we say delta H, this is basically explaining the amount of heat or energy. And because it's a positive value, it means that it's endothermic. So this slide is tricky to figure out. This is what I would suggest that you write for yourself. I'll write down exactly what I wrote for myself. Kinetic energy is heat. Why do I say that? Kinetic energy is directly related to what? Temperature, right? So if I think of it like that, kinetic energy means an increase in temperature or means increase in heat, right? Heat being given off. Kinetic energy is heat. So if it's endothermic, if it's telling me it's an endothermic reaction, or I would need to figure out that it's endothermic reaction, then there's lots of potential energy in the products. So because there's low kinetic energy in the products and high kinetic energy in the reactants, then the reactants are absorbing that energy and it's endothermic. See, endothermic means that it's absorbing the energy, right? And you get a positive value. Kinetic energy is energy in motion, which gives you that temperature increase or heat being given off or heat being absorbed, right? So if I have a lot of kinetic energy in my products, that would mean that I'm giving off heat, correct? Because as the reaction's complete, there's more kinetic energy in the product, so I'm going to see a temperature increase, which means that it would be giving heat out. But because I have low kinetic energy in my products, the kinetic energy must be high in my reactants, which means it's not giving off heat. It must be absorbing the heat, and therefore it's an endothermic reaction with the positive value. The questions that you'll need to understand are where the potential energy is stored. Is it high or low in the reactants or the products? They don't typically ask you about the kinetic energy, but just think of it as the opposite. If kinetic energy is high in one piece of this, in the products, then the potential energy is low. And I'm going to show you a slide again, but remember potential energy means that things are far away from one another. When it's high potential energy, things are very far away. When they get closer and closer and closer, they get low potential energy. So we're going to look at potential energy versus kinetic energy, which is the energy in motion. That's why in the last slide I wrote potential energy is stored in your bonds, which how far apart they are, and kinetic energy is the motion of those particles. So if I have an endothermic reaction, then I have lots of potential energy in my products, but low kinetic energy in my products. And kinetic energy is high in my reactants. You just kind of have to figure out a way to remember that. And for me, I think of kinetic energy means heat, like its temperature is increasing. So if it's in products, if I have high kinetic energy in products, then that means that it's releasing heat. If I have high kinetic energy in my reactants, then it means it's absorbing heat. That helps you. So this is just explaining the same thing again. It says because the products are at a lower temperature than the surroundings, so they were at a lower temperature because the kinetic energy was low in the products, right? In that last slide, the kinetic energy is low in the products, but high in the reactants. So since the temperature is at a lower temperature, then the surroundings are going to give heat into this reaction. So the system after an endothermic reaction has heat going to it. Heat must flow from the surroundings into the system until thermal equilibrium is established. So that means that your surroundings are going to get cold. So if you guys have ice packs, right, that you like crack. It's not exactly the same exact reaction, but it's the idea here is that the reaction, when you have an ice pack that gets cold, you are creating an endothermic reaction on the inside of your ice pack. It's a system. The system is on the inside, and the surroundings are your hands, your body, wherever you're going to put the ice pack. It's taking heat from the outside and making it cold. So when you have an endothermic reaction, your surroundings lose heat and they get cold. Do you get that? Because if you have an exothermic reaction like a hand warmer is releasing heat, and what's going to happen to the surroundings? They get warm. So if an endothermic reaction is absorbing heat, it's coming from the air, it's coming from your hands, it's coming from the beaker. It's taking heat out of the surroundings and making it cold. So the surroundings, if heat is going out, then the surroundings get cold. And remember that heat is what's flowing, not cold, right? So it's always going to either be that the surroundings are losing heat or the surroundings are gaining heat. And then after thermal equilibrium is established, everything is just going to stay the same in a closed system. All right, so if it's an exothermic process, where should the kinetic energy be high in? The reactants or the products? In the products, which means then potential energy is low in the products, right? I prefer to think of it as kinetic energy because I know that means heat. So if kinetic energy is high in my products, that means it's giving off heat, and that means potential energy is low. So as the bonds in the products contain less potential energy, the product molecules must contain more kinetic energy. This is why the products of an exothermic reaction are at a higher temperature. So since they're at a higher temperature, they're giving off heat to the surroundings, which means that it's exothermic, and you create a negative value there. So this is showing you that the system after the reaction, heat flows from the system into the surroundings until thermal equilibrium is established. And so therefore my surroundings get hot or warm, whatever you want to say. The temperature of the surroundings will increase. So this is a hand warmer. Any questions so far? All right, work and endothermic processes. So this really has to do with gases. We'll do a variety of different types of problems, but this particularly is talking about a gas in a closed system with a movable piston, which means that you're allowed to have volume changes. So a piston is something that can move up or down, right, depending on the molecules that are on the inside. So molecules on the inside are moving. And we can think of this almost like pressure. The more molecules there are, then the greater pressure there would be, right? The faster the molecules are moving, the greater pressure there would be, because pressure has to do with particles hitting the walls of the container. So if I have more hitting on the walls of my container, my pressure goes up. If I have more molecules, all traveling at the same speed, but I put more molecules in, there's going to be more hitting of the walls of the container, pressure goes up. So we're going to examine what happens to the piston depending on the particles. So it says if the pressure caused by gas particles colliding with the piston on the outside of the cylinder is greater than that of the inside, right? So this is P outside is greater than P inside. Then the gas outside does work on the piston. Energy is transferred from the gas to the piston, and the gas inside the cylinder contracts. The piston goes down. So it just means that you have greater pressure on the outside than you do on the inside, and so to create an equilibrium, it pushes down on it. And now these will have the equal pressure as of the outside. Agreed? So you'll reach an equilibrium between the two systems. So your final would have the exact same velocity vectors in a Boltzmann distribution curve that the outside does. And so we'll see a change in our volume. The same thing occurs if the inside pressure is greater than the outside pressure, then we would see that work is going to be done on the piston and to the surroundings. And so then the piston would increase. So if the pressure caused by the gas particles colliding, if pressure on the inside is greater than pressure on the outside, then we see that work is being done on the surroundings and the cylinder expands. So my velocity vectors are larger here, so there's greater pressure than there is on the outside, so it has to transfer and work is being done on the surroundings. And so then the piston increases. So we're going to look at this now to understand exothermic and endothermic reactions. Again, this is another calculation that you're not going to have to do for the exam, but you do need to kind of work through for your homework so that you understand how it transfers energy. So this has to do with work and force and the change in distance, which is our volume basically. And so our final equation is that work is equal to the negative P for power and delta V is for volume change. So we're just going to work through the questions here to understand this negative sign. If we don't have the proper sign here, we won't see that it is exothermic or endothermic. So we want negative signs to mean that it's exo, and we want positive signs to mean that it's endothermic. All right, so you're going to get a sample problem. It says a gas expands from 0.87 liters to 2.46 liters in a cylinder under constant external pressure of 1.05 atmospheres. Calculate the work associated with the expansion of this gas. So we have to go back to our equation that you just did in that last slide. And so let's look at the work equation. So work is equal to negative P times delta V. And anytime that you're doing a delta anything, right, it's going to be final minus initial. So we went from 0.87 to 2.46. So you can calculate that. So make sure that you bring your calculators for the rest of this section. You're going to use it a lot. And then you're going to plug in your pressure. I think I said power on the last slide. Pressure, sorry. So negative 1.05 atmospheres. And then clearly we're going to get a positive value for this because work is being done to the surroundings, right? So my volume expands, it means work's being done to the surroundings. What should my value of this work be, negative or positive? Because it's exo, right? It's doing work on the surroundings, so transfer is out, so it's exothermic in a sense, although this is work. If it's going into the system, work's being done on the system, then it should be endo. So we should get a negative value after solving. All right, this last part here, you do not have to know. I didn't even teach it to you yet. This is just a conversion to get you, because work is going to be in liters times atmospheres, right? Atmospheres is my pressure. My volume changes in liters, so then this is atmospheres times liters, correct? So that's not really a unit for work. Work should be in joules. So to get me a unit to go from liters to atmospheres to joules, you use this conversion factor. So this is a conversion factor. You do not have to know this. but you should apply it to your homework just so that you can see the endothermic and exothermic reactions. And so once you solve, you get negative 169 joules, which should make sense because the system should be expanding to the surroundings. So again, I'm not going to ask you to do these questions on your test or on a quiz, but I do expect you to understand if a system expands to the surroundings that you understand that that should have a negative value and it's exothermic. Do you get that? And if I tell you the work is negative, then you should know that the piston is expanding and doing work on the surroundings. All right, the next one. It says 1,142 joules of heat are added to a cylinder, which causes its contained gas to expand from 1.35 liters to 4.18 liters under a constant external pressure of 1.03 atmospheres. Calculate delta E for this process. So delta E is your energy change. So just from reading this, what is happening to the gas inside the container? Is it having work done on it, or is it doing work to the surroundings? How do you know it's doing work to the surroundings? It's expanding. The volume's greater, right? The volume is expanding. So in a sense, we're going to just say, all right, well, that's a negative value, right? However, you're supplying heat to it. Why would it expand when you're supplying heat to it? What happens to the particles? They're moving faster because if you're supplying heat to it, kinetic energy is increasing, right? So the molecules on the inside are increasing their kinetic energy, which then by default is going to increase the pressure of the inside of the container, and so it's going to increase its volume and do work on its surroundings. Everybody agree with that? However, the amount of energy that's being added to the system is going to counter the amount of energy being released to the surroundings. And so your total energy change is going to be determined by the difference of this. So you're going to look at whether or not it's going to be an endo or exo overall, not just based on the gas expanding to the surroundings. Do you understand that? There's two pieces here. Energy is being supplied in and energy is going out, and I'm going to figure out which is greater. So you're going to do both equations from the last slide and then like a bunch of slides before. So the first part is that we have to calculate work. So same thing as before that you just did in the last slide, go ahead and solve. So this is only related to my piston right now. This has nothing to do with the amount of energy that's being transferred into it. Yep. So you get negative 295 joules. All right, so this is the amount of work that's being done from the piston to the surroundings, right? So we heated up those molecules, they're moving faster, they're applying pressure to the piston, and the pressure on the inside must be greater than the pressure on the outside because the volume expands. And we expect a negative number, agreed? Because it's exo. However, there's a certain amount of heat being supplied in. So what's the equation for delta E? Delta E equals Q plus W. Q is your amount of energy being supplied into the system. So Q is the energy supplied. Now it could be that it's energy being supplied is always going to be a positive value because you're giving energy to something. So if it says that it's giving energy is added, then that's definitely going to be the positive value there. And work, you just calculated. So all we're trying to do is figure out, is the total of this system endothermic or exothermic? So you plug in your numbers. Energy supplied is 1142, work is negative 295, calculate it, and determine if this system, whole process, is endothermic or exothermic. Okay, what did you get? Yes. So is this an endothermic or exothermic process? Endothermic. Simple as that. All right, so this is just an introduction to how energy and heat come in and out of systems. We haven't even started enthalpy or understanding the calculations of actual reactions and understanding like what happens to the surroundings, the water, all that. We're just sort of introing here that energy can go into a system or it can go out of a system, and if it goes out, it's exo and it's negative. And if it goes in, it's endo and it's positive. That's sort of the takeaway for right now. So we're going to stop here, and then tomorrow we'll pick up all the enthalpy. Okay. So enthalpy is delta H. We are going to work with enthalpy, we're going to work with entropy, and we're going to work with Gibbs free energy, and they all have their own little delta letters. So delta H always is enthalpy, which means the heat of a reaction. And so we can look at delta H in terms of if it's exo, it's negative sign, if it's endo, it's positive, and that tells us which of these pieces, the products or the reactants, is in greater magnitude. So if I have more energy stored in my products than I do in my reactants, then this value would be greater than this would be a positive value. Agreed? If there's more energy stored in my reactants, then this would have a negative value. And so we did this with kinetic energy and potential energy yesterday. If there's high kinetic energy in the reactants and products, we can look at that also, and potential energy. But really, you're just going to take these numbers and you can subtract them. So high energy in my products, and then reactants, you can calculate your energy difference. And so just as a side note again, if it's positive, it's endo, and if it's negative, it's exo. This equation is given to you on your equation sheet for the AP exam. So right now, there's not that many equations that you have to actually know. We've been doing a lot of theory. So I'm just going to point out, especially even for this topic, there's a whole section of thermodynamics on here. It says thermodynamics and electrochem. There's a few of them that we're going to use for thermodynamics, and you don't have to memorize them, although you'll probably just know them. But when you get to May, all of these equations are going to end up becoming useful for you, and you may, in fact, forget how to simply just do products minus reactants. So on the exam, you are welcome to open this up and just double check it and look at it. So you're going to end up with these getting values for products, getting values for reactants, and then just subtracting them and coming up with the overall enthalpy of the reaction. So when we look at enthalpy, it is equal but opposite for a reaction. If I'm breaking bonds and I'm forming those same bonds, they are equal but opposite. So burning hydrogen fuel, this is like a hydrogen cell for your car. When we burn fuel right now, like you go fill up your tank, you get gas, you have a combustion reaction. Combustion reactions produce a lot of energy, and that energy then is used by your car to fuel your car. But you can do the same thing with a hydrogen cell. And so you take 2 moles of hydrogen gas, 1 mole of oxygen, and you create 2 moles of water, and it releases negative 572 kilojoules of heat. Your car, then, you could use this energy to power your car. The same thing is true, though, for making the hydrogen gas. So to make the hydrogen gas requires 572 kilojoules. So this process is endothermic, whereas this process is exothermic. So they're equal but opposite. So let's just talk really fast about the negative sign here. So what does this mean about my products and reactants? This is what we talked about just before with your homework. Yeah?
Your products have more kinetic energy, and your reactants have less kinetic energy but more potential energy.
That is true. And then in just a general sense, so bond forming is releasing more energy, which is the kinetic energy, than your bonds breaking, which are absorbing. So the formation of bonds releases more energy than the breaking of bonds, right? But in this case, right, when we're breaking the water bonds, that requires more energy than the forming of those bonds. So these are always equal but opposite. Any bond breaking, bond forming process is equal but opposite. So that's what this is showing you. So you release the same amount of heat that you do when you break your bonds and you absorb heat. As a side note here, if you're a chemist, you go in the lab and you're doing a reaction, This should make sense to you in just general sense now. Like you go and heat your house, or you're cold, you go turn up the heat. What are you burning? Gas in your basement? I don't know, in your, wherever you keep your heater, you're burning fuel, right? So you want the house to be 90, your parents want the house to be 75, clearly, right? Because it's going to cost us a lot of money. What happens when you burn more fuel? Why? Because you're getting more energy output, right? So if your burning fuel process is exothermic, that's releasing heat, right? That's what you're doing when you heat your house. If you burn more fuel, you get more heat, so your house gets warmer. We all agree with this, right? So when you look at this, recognize that if you put in more moles of your reactants, you get more heat out. So when you double the amount of burning or fuel or whatever you're doing, you double the amount of energy. So right on the slide, double the amount of moles, double the amount of energy. And the same thing would be true if you tripled it or quadrupled it. The more energy output is dependent upon how much of your reactants go in. All right, so this is essentially what we're doing for the next 2 lectures, probably 3 lectures for us. We're going to calculate delta H. So there's 4 ways to do this, and on the exam I will ask you, and so will the AP exam. They love thermodynamics. It's like all over the free response. They give you a variety of ways to calculate delta H. So you can either do it using bond enthalpies, which we'll do today. That's super easy. The only reason why you would ever make a mistake is like you forget to put a coefficient in, or you do like a calc error. It's super easy to do. Calorimetry is probably the hardest. That's why we're going to spend some time on it. We're going to do a lab for it, and then you'll take a quiz for it. Hess's law is like a little puzzle, and I think you'll actually enjoy doing it. And then enthalpies of formation is just a calculation that you get numbers and you put them in. So these 2 are the easiest, and then this is the hardest, and then this one's sort of in between. This is the least accurate. So really, the most accurate is the calorimetry one because this is experimental. These 2 are sort of like books, or 3 of them. You get your information from a book. So these are referenced. So is this one. And then this one is experimental. So if you are a chemist, you obviously would get the best results by doing the experiment yourself in your lab, in your conditions, and then calculating the amount of heat that's absorbed or released. The other ones give you a ballpark. So say you're going to do a reaction, and you have no idea how much heat is going to be produced. If you do a reaction that produces a lot of heat, you could be in big trouble in your lab, right? Like small scale, maybe not so much, but what if you do this times 1,000? Like you're making a massive amount of pharmaceutical drug, right? And it produces a lot of heat, and now you do that times 1,000. You're going to get a lot more heat, agreed? So you would want to calculate it sort of on paper, like, well, how much heat is this reaction going to produce? And you go look up your values, and you calculate it, and you get a ballpark so that you have an idea. Then that way, when you're going to do the actual experimental, you would know, all right, I need to cool this system down so that my glassware doesn't explode. So all of these come from books, and this one is going to be experimental. The reason why this is least accurate is because it does not take into account the states of matter. So no states of matter accounted for. So it assumes that solid water, liquid water, and gaseous water all have the same amount of energy stored in their bonds, which we know isn't true, right? Solid is rigid and tight, and liquid has more movement, and gases are far apart from one another. And so what we're talking about for bond energy is understanding the actual amount of energy stored in these bonds. So there's obviously energy stored in breaking this bond, and breaking this bond, and breaking this bond, right? Which one has the highest bond energy? The triple, right? So we're going to get a value for that, and then we're going to calculate how much energy is required to break the bonds. That's what you're going to do for this section. All right, so we looked at this again yesterday. We're going to look at it again now. But this is just recognizing that potential energy, when you're forming bonds, that's what this is talking about, your energy gets released. So you have high potential going to low, and you have to conserve energy. Agreed? So if you conserve energy, then the energy has to go somewhere because you went from high potential to low potential, and the energy gets kicked out as kinetic energy, and the temperature goes up. So this is an exothermic process because energy is being pushed out. So energy is always released during the formation of a bond, obviously, because potential energy decreases and the atoms move closer together. The same amount of energy must be added in order to break that specific bond, so potential energy increases as the atoms move away from one another. So I'm just going to write this again for you. So lost energy for this goes out into the surroundings. And then here, needed energy comes from the surroundings. All right, so anytime that you see a graph, you should always do what first? Look at the axes. They're going to be labeled for you. So we'll look at this equation in just a moment, but let's look at this in terms of potential energy. We're going to look at bond enthalpy, so the amount of energy that is being added or being released when the atoms are coming together or going apart. So here is my reaction. I have AA like this. And it's going to be going to AB, which means that my atoms are going to start pulling apart, right? So what happens when I go like this to potential energy? It goes up, right? Obviously, my little hump goes up. And then it finds B, right? And if it finds B, it's going to start forming. So what happens there? Potential energy goes down, and what happens to that energy? Turns into heat, and it goes out, right? So this is forming a bond here, and potential energy decreases. So don't call out the answer. Think about this. Is this overall process exothermic or endothermic? All right, tell somebody in your group. Okay? What do you think? Alexa? It is exo. So when you look at this graph, this is the bond breaking process. Agreed? Yeah. So breaking requires some amount of energy going in. So this is your energy in. So we know that this is positive and this is an endothermic process, right? But this is your energy out. This is the forming. So when I'm forming bonds, energy is released. It goes out, and I have a negative or an exothermic. Which process is greater? The exo. I mean, it's clear because I'm drawing you the arrow, right? Do you see that this is a much greater potential energy difference than this is? And so because of that potential energy difference, the overall process of forming an AB bond is greater than the process of absorbing energy to break the AA bond. So this reaction diagram represents an exothermic reaction profile. So this equation that we're going to use is how we're going to determine if an overall bond breaking or bond forming process is endo or exo. So this is just visually representing it, but I'm going to give you numbers in a moment, and you're going to actually calculate them. So you have to recognize that this is different than products minus reactants. We almost always use products minus reactants when we're calculating, but for this specific example, I need to know if the bonds broken are greater or less in energy than the bonds formed. So the way that you should remember this, is that B comes before A. Alphabetically, I mean F. B comes before F. So like A, B, C, D, E, F. Bonds broken minus bonds formed. And I'm highlighting this because on this exam, you're going to have to do products minus reactants, and you're going to get these confused, and you're going to flip your numbers, and you're going to get the wrong sign on your answer. You're going to get a negative when you should have a positive, or vice versa. So when I say bonds broken minus formed, what am I actually saying? Products, reactants. What's a broken one? It's a reactant. Do you understand that? So this is my reactants, and these, my formed ones, must be my products. Do you see how this is different than the equation that I just showed you? Because normally we do products minus reactants, but for this one we're going to do our bonds broken, which are always reactants. We're always breaking reactants, and we're always forming products. So think of it that way. It's alphabetical, B before F, bonds broken minus bonds formed. Okay? So the only thing that this equation is missing is that I like to put a little n in here because we're going to have to use the coefficients in the reaction. So we balance a chemical equation and it says I have 2 moles of hydrogen gas, then I'm going to have to incorporate the number of moles in that equation. So put a letter N to calculate moles. All right, so if something is exothermic, same thing I'm talking about here. More energy is released during the formation of bonds in the products than is required to break the bonds in the reactants. And the products are at a lower potential energy than the reactants, which means that they are at a what? Higher kinetic energy, right? That's how I get an exothermic, is when the products are at a higher kinetic energy. So on your questions tonight, and any questions that I ask you, sometimes, and you saw one of them last night, I think question 6, it's just asking you to describe the process. Why is it endo or exo? And anytime it asks you to describe that, you need to talk about which is trumping the other, bond forming or bond breaking. And then that explains why the value is negative or positive. So it's this sentence here that gives you that explanation, and then obviously the same sentence for endothermic processes. So on this graph, on this slide, can you draw me the potential energy reaction profile for an exothermic process? We just did that. I meant for an endo, this slide. So the next slide is endothermic. So this one, hold on one second so we correct this. If this is endothermic, it says the products are at a higher potential energy than the reactants, and they have lower kinetic energy if it is endothermic, right? Yep.
The energies of the processes, are they equal?
Only for the same thing. Equal but opposite would be for the reverse of the same exact reaction. But when I'm doing AA breaking apart, that's a different type of bond than AB forming. So they wouldn't ever be the same. But you don't make the same products that you had as your reactants. So you're always going to have different values. All right, so on this slide, I'm asking you, can you draw me your reaction profile for this is the reaction progress going this way, and this is your potential energy going this way. So draw that hump thing for an endothermic reaction. What should it look like?
A hump, but the first hump's bigger than the second down. I'm sorry.
I'm humping. I'm humping. I'm starting my hump.
When it comes back down, it doesn't go lower than the initial.
There we go.
Yes, did we draw that?
That's the hump.
Yeah.
That's the hump. I did just say that. Excuse me. All right. So it should be obvious here that the breaking bonds has higher potential energy than the releasing bonds, right? So if I have greater energy to break bonds, that means greater energy is used to absorb than to release, and so then the value is positive and it's endothermic. But that comes from you understanding that bond breaking is always endothermic because you're always absorbing energy to break bonds, right? You have to have that fundamentally stuck in your head from now on. Just stuck there. And it's karate chopping. It's like a wooden block. You're trying to karate chop that wooden piece of wood. and you karate chop, you have to absorb energy into the wood. All right, so now we're going to calculate bond energies, bond enthalpies. So when we use this equation, we're going to calculate individually the amount of energy stored in the bonds. And remember I said that this is not accurate because it's not telling me if the bonds are in the solid, liquid, or gas phase. So in order to do this, I have to physically look at the structure of the molecule to know what kinds of bonds I have. So I have to draw all of these. So if you get an exam question that asks you to calculate these, and yes, these will be multiple choice questions, you have to be able to draw the structures, so you have to remember how to draw, and you have to also know how to do some sort of quick math and come up with the correct answer. Not exact answers, but a roundabout answer. So if I'm going to do this, I'm going to do the sum of my bonds broken minus the sum of n, my bonds formed. All right, so bonds broken are always going to be my reactants, right? So I have CH4, and I have O2, right? And then this is going to go to CO2 and H2O. All right, so I'm going to calculate now by looking at the bond enthalpies that they give me in the chart. You always will get a chart of some sort. If they don't give you a chart, they'll tell you the numbers. If you're doing this as a chemist, you go look up your numbers in a book. So the first one, bonds broken. How many CH bonds do I have? 4. So I always start with a big bracket so that I group my bonds broken together. So I'm going to do 4 times, and then CH is 413 kilojoules. Plus, how many O double bond O's do I have? 2, because the coefficient says 2, right? There's actually 2 of these. So if I count them, I have 2 times my O double bond O is 495. And then I bracket that and I put a subtraction sign. Now my bonds formed are always my products, right? I bracket that. And I have 1 CO2 molecule, so how many bonds do I have of C double bond O? 2, right? Because there's 1 here and 1 here. So that's 2 times, and C double bond O is 799. And then this is plus, and how many H2O molecules do I have? 2, so how many bonds? 4 bonds, because I have 2 of these molecules, so that's 1, 2, 3, 4 bonds of them. So 4 OH bonds, and that's 467. Literally just throwing this in your calculator and getting the right answer. And then on a multiple choice, you'd have to do this in your head for sure. But you should be able to handle that. That shouldn't be too difficult for you. All right, so take a moment and put it in your calculator, and then we'll check the answer. So you throw it all in, and you get negative 824. And make sure you have units, kilojoules per mole. You get your units because in the question, it showed you the units for each of these bond enthalpies. So you're just going to put that right in there. Make sure that you include units. So on the exam, my expectation is that you have sig figs, correct, and units. Definitely units. I think I mentioned yesterday that the AP exam usually looks for sig figs in one spot. Did I tell you this?
Yeah.
Okay. And then the same thing, definitely for units. Like 10 times more often do they check for units than they do for sig figs. Sometimes it'll even say with the correct units. So in order for you to get an answer correct, you might get 1 point issued, but it'll say the correct answer with units. And that's how you'll get your 1 point. If you don't write your units and you just wrote a number, you don't get the point. So include all your units. All right, the next question is just using some algebra. So it says calculate the average bond energy in an H-H bond. Clearly I could look it up, but what if I didn't? I can use the answer, which is giving me delta H, and set the rest of it equal to delta H and solve for X. So algebraically, you're going to go and solve for this. So the answer is 401 kilojoules per mole.